Okay, and now I want to start. So today I want to present my report, which is named Formation, Evolution, Collapse and Applications of Correlated Packets in Low-Energy Nuclear Reactions Experiments. Traditionally in quantum physics, in different experiments, when we are talking about particle which is moving, we are using formalism of quantum mechanics, and we are describing this particle, slow-moving particle, as an unbounded in space plane wave. So we can write a Schrödinger equation for this particle. This is a very simple equation of a plane wave. For example, such equation can be written for slow proton with a small energy of 100 to 100 electron volts. But such approach is idealized. It is impossible to say that proton is a plane wave. Of course, it is better to use some more complicated and quantum mechanical analysis to describe this particle, and it is better to use so-called approach of packets. We can describe motion of particle in the form of normalized Gaussian wave packet, which are described by a wave function which has initial structure. Here you can see this structure. This is a usual Gaussian structure, and this particle is moving in space, and it changes the amplitude of this particle, the form of this particle, the form of this wave function changes during its motion in time. We have some initial equation which describes initial state of this particle. We have some initial form of this particle which is moving, and we can easily calculate the form of wave function during any moment of time and any place. If we know mass of this particle, time, momentum of this particle, and if we have this momentum, we can calculate the energy of this particle. This formalism can be used not only for a packet of particle, a beam of particles, but this formalism can be used even for a single particle. So we can present a single particle as a Gaussian packet which is moving in space. It is very easy, it is very easy to achieve such formula. We can make very simple quantum mechanical calculations. We can write an equation for expansion of wave function by plane waves. Each equation of plane wave has such form, and every plane wave has its own amplitude. These amplitudes can be found by this equation. This equation describes the amplitudes of plane waves, which means Fourier components of our wave functions on different momentum. And if we use these Fourier components and put them in this equation, we can find the wave function for Gaussian packet. It is the wave function which I have already presented on previous diagram, on previous slide. You can see here. That is not very simple. That is not anything new. This result can be found in any textbook on quantum mechanics. I think so. And we can find the evolution of this wave packet. The evolution of this packet is also very simple. This packet is spreading. The longitudinal coordinate of this packet, the width of this packet, is increasing, and the amplitude of this packet is decreasing. And we can find the amplitude on time. We can see that with the time increase, the amplitude of this packet is decreasing, and the width of this packet is increasing, which means that it was a great packet, and then it spread out, and the amplitude increased. It is very good, but nothing new. So we can see the evolution of this wave packet. At the beginning, it had high amplitude, and it was small in width, and with its motion, the amplitude decreases, and width of this packet increases. We can find the initial dispersions for coordinate and for momentum for such packet. We can find that they are connected with its width, and we can find that at the initial moment for this packet, we can write traditional standard Heisenberg uncertainty relation. Also nothing new. But for the purposes of low-energy nuclear reactions experiments, it is much better to use so-called correlated wave packets. What is the difference between correlated and standard wave packet in the formalism of quantum mechanics? At the beginning, correlated and uncorrelated wave packets have the same form, Gaussian wave packet. But if we watch on this function, we can see that in this expression we have a new coefficient g. This coefficient depends on correlation coefficient R. What is correlation coefficient? It was already described in previous report tomorrow in the morning. So this correlation coefficient, I will regard it on the next slide. But the appearance of correlation coefficient in this equation greatly changes the evolution of this packet during its motion in time and space. And our aim was to find this evolution and to propose, is it possible to use such packets for the purposes of low-energy nuclear reactions experiments, and how it is possible to create such correlated packets. Because it's very easy to say, let's have correlated packet, but how we can create this packet, what does it mean we have? Such packets are characterized by correlation coefficient. This correlation coefficient R, it is connected with this coefficient in this equation, and at the beginning they have identical space structure. So this imaginary part disappears, and at the beginning everything is the same. Also, this is a result which has already been presented today in the morning. Correlation coefficient is some value which is connected with dispersions of two values A and B, and product of these two dispersions depends on this correlation coefficient and uncertainty relation for these two values. For example, momentum and coordinate depends on this correlation coefficient, and this product is much greater, can be much greater than in the case of uncorrelated packet in G times, where G is the coefficient of correlation efficiency. The greater this coefficient, the greater is the product of these two values. And we have correlated packet. This correlated packet moves in space and time. It is easy, it is possible to find wave function for correlated wave packet. To find these wave functions, we can do the same as we have already done for uncorrelated wave packet. We can write a relation which is connected with the amplitudes of Fourier components, of amplitudes of plane waves. We can find a component for this plane wave in every state. For correlated packets, wave functions can be calculated. We can find it. We can use this expression, the amplitude of every component, Fourier component of every plane wave in this equation. We can find this integral. This is component, this is integral, this is total wave function of correlated wave packet. And we can find, it is a little bit great, an equation which describes correlated wave packet. So we can analyze this equation, and we can analyze the behavior of this packet during its motion. What is the main? The main idea is, as I've already told you, that during its motion it is not only spreading in space and decreasing in amplitude. Its evolution is much more complicated. Not here. From the analysis of this expression follows that during the motion of correlated packet, evolution of its structure is more complicated. It differs correlated packet evolution from the monotonous spreading of uncorrelated packet. We can make analysis and we can see that at the beginning these packets have the same form, but during its motion the amplitude of correlated packet decreases greatly at some place, and later it is returning to the initial position, and after some time correlated packet becomes even wider than uncorrelated one. So we can see that in specific place, this place can be calculated if we know parameters of this packet. A collapse of wave function of uncorrelated wave packet takes place. It can be seen, this is the result of calculation, and it can be seen this is some kind of diagram that we have initial wave packet, we have some collapse, and we have decrease of wave function. Also, this result is presented on this figure. So with time increase, for uncorrelated wave packet, we have only spreading of size and decreasing of amplitude. When we have correlated wave packet, we have increase of amplitude in some place, which means collapse of packet in some place in space and time. And after this collapse, its amplitude decreases greatly. This is the result of calculation. This is density plot, which describes the amplitude of correlated wave packet on space and time. And we can see that really this collapse takes place in one point of space and time. Before we have white packet, then we have collapse, and then its amplitude increases and it becomes white. It is possible to use this point, this dot, for different purposes. We can calculate the amplitude of this wave packet. We can calculate how it depends on time. We can calculate the time which is needed to make such collapse. If we know this time, we can find the minimum width of this packet. And this width is g times less than the initial width of the packet. If we have g equal to 10 power 4, 10 power 5, then we have a great decrease, a great squeezing of this packet. And after the collapse, the width is increasing in g times. So we have squeezing and spreading. We can compare it with uncorrelated wave packet, where there is no such coefficient. And the same for amplitude of this wave packet. We can calculate, if we know time of collapse, distance where collapse occurs. If we know this distance, we can calculate wave function, and we can show that wave function in this place is g times greater than the initial wave function. So beam is collapsing in one point and then squeezing. And we can show that after this collapse, the amplitude is decreasing very fast. We can also find average value of momentum and momentum dispersion, and we can show that the amplitude of energy fluctuation is g times greater than this value, g times square greater, which means at this point we have a great increase of uncertainty of energy. In this place where we have collapse, if this packet is correlated, the uncertainty of energy allows us to receive at one point energy which can be thousands, hundreds times greater than the energy that this particle have. Uncertainty is thousands times greater than the energy. So, for example, if we have uncorrelated proton, the width of this, if we represent uncorrelated proton as wave packet, the width of this packet is nearly 1 angstrom. For example, we have low energy. Uncertainty of this proton in uncorrelated state in 10 power minus 3 electron volt. If we have correlation coefficient of correlation efficiency 10 power 4, that we have uncertainty of energy 100 kilo electron volts, which means that for one moment this proton can receive very great energy, and it can be used for the purposes of reactions. This proton has low energy, but uncertainty of its energy allows us to use it in nuclear reactions. And we don't need acceleration to receive great energy. Such energy exceeds the average energy of proton longitudinal slow motion in low energy nuclear reactions experiments, where average energy can be equal to several units or tens of electron volts. So, proposed scheme, how it is possible to use it, we can compare with traditional scheme. Traditional scheme, what do we have? We have beam source. Beam source is generating low energy particle beam, uncorrelated. Then we have some accelerator. Accelerator is a great facility. In this accelerator, these particles are accelerated. We have high energy particles beams, uncorrelated. They interact with target, and we have some nuclear reactions. In our case, we have same beam source, we have the same low energy particle beam uncorrelated, but we do not need great accelerator. We can't build accelerator in our small laboratory. We need system of correlation formation, where correlated packets are formed. After this system, we have the same low energy particles beams, but they are correlated. They are moving towards the target, and they are interacting with this target only in a small layer after the T collapse after the formation on the distance x collapse from this system. On this distance, in this moment of time, we have a great correlation coefficient, we had a great decrease of energy uncertainty, and we have a possibility of energy release and low energy nuclear reactions. For example, if at the beginning we have 0 coefficient of correlation and equal to 1 coefficient of correlation efficiency, if in this place it is much greater than 1, then the energy, uncertainty of energy can be much greater than it was at the beginning, and we have collapse, and we have great energy release, and we have a possibility to create energy reactions. This action occurs only in a thin layer. It doesn't occur there and it doesn't occur there. So we have to build our system very precisely. So how it is possible to build such correlated packets? The main idea, it was already presented today, is modulation of parameters of a quantized system within which the particle is located, gives us a possibility to make such correlation. For example, we can have a quantum oscillator, and we can modulate this quantum oscillator. And during this modulation, the correlation between wave functions in different states appear, and this correlation allows us to create coefficient of correlation and to form correlated wave packet. During such modulation, phase correlations between wave functions in different states appear, and this system can be of different nature. It can be a real field of some quantum system. For example, it can be a field of crystal in which a channeling particle is moving. It can be a field of some magnets, and interaction of magnetic field with charged particle also allows us to create such system. It can be any system that is suitable for these purposes. It can be some dynamic structures, nanocracks, and etc. So, for example, some systems that we want to propose. First system is a system of magnets. For example, if we have some particle, which means proton beam, and this proton moves in the system of magnets which are oriented in such a way that magnetic field changes, we have an amplitude, we have an oscillation of this charged particle in magnetic field. We can find the frequency of this oscillation. It depends on the amplitude, reached amplitude of this field. And if we know this frequency, we know that the frequency of the interaction is modulated. In some places, the field is great. In some places, there is no field. So we have some modulation of this frequency. We have some changing frequency of oscillator with changing frequency. And in this case, it is possible to form correlated state, and it is possible to form a correlated packet. In the case of free packet motion, such a state can be formed during periodically in homogeneous perpendicular magnetic field. We can calculate parameters that we need. We can take typical magnets. Typical magnets have a field of nearly 10 kilo-oersted. If we take such field, we can calculate the frequency which is connected only with this field and with the nature of the particle which we are using. For example, proton. We can calculate this frequency. This frequency depends on this amplitude. If we take, for example, such parameters, we can take some velocity of the particle, we show that this system would be optimal for protons with energy of several kilo-electron volts. And unfortunately, this system has some lacks. For example, in our article that was published in Journal of Experimental and Theoretical Physics, it was shown that such modulation is not very effective. During such modulation, we have an increase of parameter of correlation, but also in such system we have an increase of amplitude. So we are not only forming correlated states, but we are also giving energy from our system to our oscillator. It's some kind of accelerator. It is not very good, and the maximum coefficient of correlation, which, as it was shown, can be made in such system, is nearly 0.98. It is not so great. The coefficient of correlation efficiency is only 5. We need greater. For our purposes, we need coefficient of correlation efficiency 10 power 4, 10 power 5 to make a really great uncertainty of energy for our reactions. So it is much better not to use such system with such way of change of frequency, but to modify it and to use a small modulations of frequency when we have some constant frequency and this frequency changes with some small coefficient. It can be an oscillator with changing amplitude or with changing widths. Both ways allows us to create correlated packets. And it was shown in our previous articles that in this case we have very fast increase of correlation coefficient, but only on several frequencies. We can show that if frequency of modulation is equal to the frequency of oscillator, we have a great increase of correlation coefficient, and during several periods it has a value 0.999 or even 0.9998, depending on time. Depending on different coefficients of modulation depths. And it was shown that for such system, the greatest efficiency is when frequency of modulation is either equal to the frequency of oscillator or 2 times greater. This is the dependence of averaged correlation coefficient on frequency of modulation. On other frequencies, effect of correlation formation does not occur. And so we need such type of modulation. I have 3 minutes. We know that the optimal value of modulation is in the case when the modulating frequency is 2 times greater than the frequency inside this oscillator. And we propose to use periodically changing magnetic field. For example, we can use a coil, and parameters of this coil are modulated with modulation parameter G. For example, during its motion, in some places this field is greater, in some places this field is smaller. We have motion longitudinal, we have motion perpendicular. This perpendicular motion is quantized, and we have oscillator in perpendicular direction. We have quantized states with some wave function, with some momentum and some energy. We have modulation of field. This modulation of field, for example, let's take field the same as it was in the case of standard magnets, for example, 10 power 4 Ørsted. If we know this field, we can calculate the frequency, 10 power 8 seconds minus 1. If we know this frequency, if we take protons with energy 200 electron volts, we can calculate their speed. If we know this speed and we can calculate the distance which is needed, the period of this coil, and we can find this period, the frequency of this relation with this coil has to be 2 times greater than the frequency of oscillations. And we can easily find that the period of this coil for such parameters has to be nearly 1 centimeter. Of course, if we change the magnitude, if we change the amplitude of our field, we can change these parameters. And it was shown that for formation of great coefficient of correlation that is equal to 10 power 4, 10 power 5, we need omega t is equal to 50, 60. it is formed here, not at the beginning, but after some time. After some time means that on some distance, and the number of periods which is enough for formation of such system shows us that the length of this coil has to be nearly 1 meter. So the parameters are quite realistic. That is not something fantastic. Amplitude of field, period, length of our coil. My time is ended, so I want to go to conclusion. Conclusion. Considered above features of the correlated wave packet make it possible to predict the possibility of its use for a number of applied and fundamental problems. Along with the collapse on a specific distance, the creation of such a packet is accompanied by a significant increase of its kinetic energy fluctuations, which can be many orders of magnitude higher than the average motion energy of the packet itself. It may allow to use them for nuclear reactions even at low particle energies. The importance of correlated states and their fundamental difference from uncorrelated superpositional states is the following. Such states may have great fluctuations of energy that can exist for a long time without violating the law of conservation of energy. Thank you.
How are we going to comment this actually collapse time and collapse point in terms of the magnetic field coming from the spin of the particle? Is it going to increase intensity of this magnetic field at the point of the collapse, at the time of the collapse, or no?
We haven't calculated the influence of spin on these processes, so I can't answer your question. But I don't think that it would influence in some way. I don't think so. Spin of proton is small enough, and magnetic field is not so strong.
I'm not a theoretician, so I have a hard time following all the calculations. But physically speaking, are you talking about a large number of deuterium atoms or something like that? What's happening physically?
This formalism can be applied either for one particle or for a whole packet of particles. There is no difference which particles we are talking about. I was talking about proton as an example. We can take about proton, we can talk about deuterium or any other particle. It doesn't matter. The parameters of our system, of course, changes, but this change is not something that affects the main conclusions. So this formalism can be applied for any types of particles.
Mm-hmm. So if I imagine a capacitor, you know, with many particles inside, and I put a pulse with a drifting frequency, you know, may I get something?
Changing frequency of capacitor and motion of particles inside this capacitor? I think yes, because capacitor, if capacitor changes, if capacity changes, the energy changes. If the energy changes, we have some oscillations of parameters of oscillator, and then coefficient of correlation may change. So I proposed only some types of possible wave realization, but other types are also possible. I don't think that it's just something principle.
May I? So this effect works also for electrons?
Yes, of course, this effect works and for...
And my stupid question, why nobody tried to use for the usual particle accelerator we have a lot of dissipation, Bremsstrahlung and so on. So I cannot imagine. Your idea seems wonderful. Why nobody think about? To apply.
I can't.
Because Bremsstrahlung emission of electrons is the most dangerous, most problematic to have electron beams that are extremely useful. So maybe you can propose. So it seems too much nice to be true.
too much nice to be true.
Sorry.
Unfortunately, I can't answer why nobody has made it, but we have proposed. I think that's a simple enough idea, so it is possible to check it, to take some real parameters and to check for electrons, for example.
You make some small experiment, some beginning experiment, or just idea?
No, we have no experiments. That is a new result. We haven't checked it. That is the question for future.
So, okay. I hope it will work well.